I welcome all of you to the class. As far as today's class is concerned, today we'll be talking about the drawing of shear force and the bending moment diagrams. Now, I will be solving this example 6.1 for you, and from this example, then onwards, I will be drawing some conclusions which will be very important for drawing the shear force and the bending moment diagrams for other type of beams as well. So, the lecture is about drawing the shear force and bending moment diagrams. The type of beam we have a simply supported beam. We say a simply supported beam is a beam which is having a pin support at one end. When I say a pin support means that is if you apply a load here, the beam will rotate about an axis passing through this point. Let me call this as point A. Okay, that is if you apply some load, the beam will rotate like this. Okay, so it will have some angle of rotation. But here at the pin there is no translation. At the pin there is no translation. The beam does not translate, but the beam rotates. So beam has rotation, but the beam does not have translation. That support is called a pin support. And on the other end, we are using what's known as the roller support. As far as the roller support is concerned, the roller support is the support at which the beam translates. That is, if you have a roller like this, if you have a roller, then what this roller will tell to do, if you apply a force in this direction, then this roller will move in this direction. So at the roller support you have translation, there is translation, but at the roller support there is no rotation. Okay, it does not rotate. There is no rotation, but yes, at the roller support there is translation. That's very important. So when we talk about this a beam having a pin support at one end and a roller support at another end, such a beam is known as a simply supported beam. So we call this beam as a simply supported beam. This is what we call as a simply supported beam. Now in this simply supported beam, let's suppose we have applied a uniformly distributed load, UDL. A uniformly distributed load has been applied such that the intensity of the load is uniform, that is W. And the span of the beam, that is the length of the beam, is, say for example, equal to L. Now what will happen under the influence of this load W, which is a uniformly distributed load, so its load diagram will be in the form of a rectangle, okay, such that the length of the rectangle will be L and the width of the or height of the rectangle will be equal W. Now this is load is given as Newton per meter or kilonewton per meter. Okay. Now what will happen under the influence of the load? These supports, the tendency of this load will be to move these supports down. But for this beam to be in equilibrium, these supports will generate the reaction. And the reaction at the support will be in this direction. We say this is reaction at end A, and we say this is reaction at end B. We'll be calling this as RB. Okay. Apart from this, uh, at any cross section of the beam, if you draw a cross section at any point, at any section or at any point of the beam, okay, then the left portion of the section has to be in equilibrium with the right portion of the section. Okay, so that is possible. The equilibrium is possible when at any section summation of all the moments has to be equal to 0 and summation of all the forces at that very section has to be equal to 0. The moments that are generated across the length of the beam, we call them as the bending moment. And at any cross section of the beam, the force that is generated, we call that as the shear force. Okay, so we have to find how the shear force varies along the length of the beam and how this bending moment varies across the length of the beam. And then we'll be plotting them. That's what we call as a shear force and the bending moment diagram. The first and foremost step while you draw the shear force and the bending moment diagram is to find these reactions RA and RB. So first step is writing the equations of writing the equations of equilibrium. So when we write the equations of equilibrium, we treat this to be our x-axis, this to be our y-axis. So it will be RA plus RB, and you have load acting in downward direction, okay, and its intensity will be its magnitude will be its intensity, that is W multiplied by L, because we know from mechanics that the uniformly distributed load can be represented by their a single load whose magnitude will be equal to the area under the load diagram, okay, that is W into L. So this is equal to 0. Therefore RA plus RB is equal W into L. We call this as equation number 1. Okay. So what we have done, we have essentially represented this force in terms of RA and RB. Okay. Number 2, let's take point A. Summation of all the moments about an axis passing through point A has to be equal to 0 for equilibrium. Okay. So first moment will be because of RB. Its magnitude will be RB multiplied by L, and it's trying to rotate our beam in anti-clockwise direction. We'll be taking it as positive. RA will generate no moment about an axis passing through point A. Okay. The second moment will be because of the uniformly distributed load. Okay. And it's the entire force, this entire load can be assumed to be acting at the center of mass or the center of gravity or the centroid, what you call as centroid, okay, such that the magnitude of this load will be equal to the area under the load diagram, that is W into L, and the centroid of this rectangle is at a distance L by 2 from the end A. Okay, therefore the moment because of this load will be W into L multiplied by the force arm, that is L by 2, and it's trying to rotate our beam in which direction? It's trying to rotate our beam in clockwise direction. We'll take this as negative. This has to be equal to 0. Therefore RB becomes equal to WL divided by 2. We'll call this as equation 2. Now from equation 1 and equation 2, RA will be equal WL minus RB, that is WL minus WL divided by 2, that's equal WL divided by 2. Therefore, as far as RA is concerned, RA is also equal WL divided by 2. So we have got it, RA is equal WL divided by 2 and RB is also equal WL divided by 2. So while you draw the shear force and the bending moment diagram, the first and foremost step that we have to do is to find the values of these reactions which we have obtained. We have obtained RA is equal to WL by 2 as well as RB is equal to WL divided by 2. Now, once we have completed it, what we have to do then? We have to, for drawing the shear force and the bending moment diagram, we will be using first the method of sections. So as far as the method of sections is concerned, in the method of sections, we have to draw a section at any point of this beam. So how we draw the section, that's important for us. So as far as draw a section at any point, let's suppose this is here. Take a section, draw a section at any point of this beam such that the distance of the section from this end A is, say for example, X. Okay, so once you draw the section, you will get a beam portion like this. We have obtained a beam portion like this, such that at this end we are having a reaction RA is equal WL divided by 2. Okay, this length where we have taken the section is equal to X. Okay, now what you will do, the point where you have taken this section, say at this very section you are having shear force V and you are having bending moment equal to M. Okay, why we are writing shear force here is equal to V? I have answered this question in the previous lecture. Because this portion of the section, this portion of the beam will be in equilibrium with this portion of the beam. Okay, so if you have a shear force here V, then this other end will have the shear force like this V, such that the resultant shear force at this end will is equal to 0. In the same way, at any section there will be the bending moment which will be balanced by another portion of the beam, such that the resultant bending moment at any point of the beam will be equal to 0. The question is why bending moment? Because the tendency of this load is to bend the beam as well. Okay, so the beam will bend essentially like this. What you call as the beam deflects like this. Okay, So the beam has undergone some angular displacement that we call as theta. So this angular displacement is possible only when you have some bending moment. Now we have to find this m as well as this v. So once you have taken the section, again write the equations of equilibrium. The equations of equilibrium will be summation of all the forces in this section has to be equal 0. Okay. So when you went on to find write the equations of equilibrium, you have v acting in negative y direction, that's minus v. You have Ra acting in upward direction, that is Ra, and the intensity and the magnitude of this load because of the uniformly distributed load of magnitude W, intensity W acting over distance x will be minus Wx is equal to 0. Therefore, this V becomes equal to Ra minus W into x. Therefore, shear force becomes equal to Ra, that is W, L by 2 minus W into x. That's equal W into L by 2 minus x. This is shear force. This is how the shear force varies. The shear force varies. The equation, this is the equation of our shear force. I will write this as, this is equation of shear force. So I will write it here. The equation of shear force is V is equal to W L by 2 minus x. Okay, this is the equation of shear force. Now let's talk about the bending moment equation. As far as the equation of bending moment is concerned, and in the same section, take summation of all the forces about an axis passing through point A equal to 0. That is, use summation of all the moments about an axis passing through point A should be equal to 0. Therefore, we are having the anticlockwise moment m, which will be taking positive, whose magnitude we have to find, and we have the moment because of the shear force, it is trying to rotate the beam in clockwise direction. Its moment will be minus v into x. Okay, its moment is equal to minus v into x, and the moment because of this uniformly distributed load acting up to a distance x, you can replace this entire load by a single load whose magnitude will be w into x acting at a distance x by 2. Therefore its moment will be minus, because it's trying to rotate the beam in anti-clockwise clockwise direction, it is wx into x by 2. This is equal to 0. Therefore m becomes equal, as far as m becomes equal, m is equal uh, wl sorry wx square by 2 plus v of x plus v of x. Okay, now this v is shear force. If you apply the equation of equilibrium on the section, you will find Ra minus v is equal to 0. Therefore v becomes equal to Ra, which is equal to wl divided by 2. So we can write m is equal wx square by 2 plus v is equal wl divided by 2 into x. Okay, therefore that becomes equal m becomes equal w by 2 x square plus l into x. So I will write here, as far as the bending moment is concerned, m is given by w by 2 into x square plus L into x. Okay, so you see v is a function of x, therefore we also write this as v as a function of x. M is also a function of x, we write this as m as a function of x. Okay, now this is how the shear force and the bending moment varies. Now what we have to do, we have to plot these shear force and bending moment. So you return back to your diagram, okay. So draw this axis, this is your one axis. Okay, draw another axis. Okay, draw another axis. This. Okay, this is where x is equal to 0. This is x is equal to L. This is also x is equal to L. This is x is equal to 0. Along this axis, you plot positive V. Along this axis, you plot minus V. Along this axis, you plot plus M. Along this axis, you plot negative m. Okay. So what will essentially happen? First of all, take the shear force. As far as the shear force is concerned, how the shear force will vary is, this is our x is equal from here, take the points. This is x is equal to L by 2. This is x is equal to L by 2. Now see, at x is equal to 0, okay, at x is equal to 0, v becomes equal WL divided by 2. So x is equal to 0, v is WL divided by 2. So it is here, okay. Then at x is equal to L by 2, when x is equal to L by 2, L by 2, L by 2 cancels, v becomes equal to 0. So at x is equal to L by 2, v is equal to 0. Now when x is equal to L, when x is equal to L, it is L by 2 minus L. That is, that becomes, v becomes equal to minus WL divided by 2. This is WL divided by 2, minus WL divided by 2 will be this direction. So this is minus WL divided by 2. And join all the 3 points with a line. Therefore, this line represents, this diagram represents your shear force diagram. Okay, this is positive V, this is minus V, and this diagram is called the shear force diagram, SFD. Okay, now similarly take the bending moment. Now use the bending moment equation. At x is equal to 0, at x is equal to 0, the bending moment is, at x is equal to 0, the value of the bending moment m is equal to 0. Okay, at, okay, this is m is equal to my vx, and this is also wx. This is clockwise. Okay, fine. So in the same way, you can plot the values of this time. You can, now let's plot the value of this. There was an error in the equation, so here we have to correct it. We'll write m is equal wx square by 2 plus, in place of this v, we have to write w L by 2 minus x, and we have this x. Okay, that's what we are writing. So this becomes equal w x square by 2 plus w lx by 2 minus wx square. So as we solve it, let me clear this my space to write it. So as we'll write this, m now equal, this will come out to be equal, m will become equal, first of all we have this w lx divided by 2, then we have wx square by 2 minus wx square, that is minus wx square divided by 2. Okay, so we can take w by 2 out. What will be inside? It will be lx minus x square. Okay, so this is our bending moment m. So I have to make a correction here now, as I will write the value of this m. The value of this m is, the bending moment m is equal uh, w by 2 multiplied by lx minus x square, lx minus x square. That's okay. Now see, at x is equal to 0, the value of bending moment is equal to 0. So our first point is over here. So this is the point. Okay, at x is equal to L, so this becomes L square, this becomes L square, and m again becomes equal to 0. So this is 0. Okay, at x is equal to L by 2, the value of m becomes equal w by 2 into L by 2, that is L square by 2 minus L square by 4. Therefore, that is w L square uh, by 8. This is m. So at x is equal to L by 2, it is positive, it is WL square by 8. Okay, and this is an quadratic equation, this is a parabolic equation. Its entire graph will essentially be like this. Okay, this is positive m. So this is known as bending moment diagram. So this is shear force diagram, and this is the bending moment diagram. Okay.